There's a moment in science when the impossible becomes possible, when the very act of asking a question changes everything. Picture this: a group of astronomers, armed with little more than telescopes and sheer determination, setting out to measure nothing. Not emptiness, not darkness, but the absence of something so fundamental it defied belief. They weren't just staring into the void. They were challenging the universe to reveal its secrets, even if it meant risking everything: their careers, their reputations, even their sanity. This is the story of those who dared to measure nothing, and in doing so, unlocked truths that reshaped our understanding of reality itself. It's easy to forget how much courage it takes to confront the unknown. These scientists weren't just facing the vastness of space. They were up against skepticism, ridicule, and the crushing weight of conventional wisdom. Imagine standing at the edge of human knowledge, peering into the abyss and whispering, "What if? What if the universe isn't what we think it is? What if the empty spaces between stars hold the key to everything?" Their journey wasn't just about data or equations. It was a battle of wills, a test of faith in the scientific method itself, and the stakes couldn't have been higher. Today, we take their discoveries for granted, but their legacy is anything but ordinary. Their work didn't just fill textbooks, it rewrote them. It's a story of obsession, of late nights under cold desert skies, of heated debates in hushed lecture halls, and of moments so profound they bordered on the spiritual. This isn't just a tale of science, it's a testament to the human spirit. So let's step into their world, where the line between madness and genius blurs, and where the pursuit of nothing led to something extraordinary. By the end, you'll never look at the night sky the same way again. Measuring nothing might sound like a contradiction. How do you quantify emptiness? But in astronomy, the absence of something can be just as revealing as its presence. Think of it like listening for silence in a crowded room. At first, all you hear is noise, but if you focus, that silence, where there should be sound, tells you something's missing. That's what these astronomers were doing. They weren't just staring at blank patches of sky. They were tuning their instruments to detect the universe's whispers, the faint echoes of what wasn't there. Take the cosmic microwave background, for example. It's the afterglow of the Big Bang, a faint hum of radiation filling every corner of space. When scientists first detected it, they weren't looking for light. They were trying to explain why certain parts of the sky seemed unnaturally quiet. That nothing turned out to be the oldest signal in the universe, a snapshot of creation itself. Then there's dark matter, an invisible force that doesn't emit light or energy, yet its gravitational pull shapes galaxies. Astronomers didn't find it by seeing it. They found it by noticing stars moving in ways that shouldn't be possible unless something unseen was tugging at them. This is the paradox of measuring nothing. The universe speaks loudest in its silences. Every gap, every unexplained absence is a clue waiting to be decoded. These scientists weren't just chasing shadows, they were reading between the lines of reality, uncovering the hidden rules that govern everything. And in doing so, they proved that sometimes the most important discoveries aren't about what's there, but what isn't. To understand how far we've come, we have to go back to the beginning, to the astronomers who first dared to ask, what are we missing? Imagine living in a time when the Milky Way was thought to be the entire universe, when the idea of other galaxies was dismissed as fantasy. That's the world Edwin Hubble confronted when he aimed his telescope at the Andromeda Nebula. Most scientists believed it was just a cloud of gas within our own galaxy, but Hubble saw something different. By measuring the flicker of distant stars called Cepheid variables, a technique pioneered by Henrietta Swan Leavitt. He proved Andromeda wasn't part of the Milky Way at all. It was another galaxy entirely, millions of light years away. Overnight, the universe exploded in size, and Hubble's discovery shattered centuries of assumptions. But these breakthroughs didn't come without risk. Leavitt, a woman working in an era when female scientists were often sidelined, spent years meticulously cataloging stars at Harvard Observatory, unpaid for much of her career. Her work on Cepheid variables became the yardstick for measuring cosmic distances, yet she rarely received the credit she deserved. Hubble, too, faced skepticism. His radical claim that the universe was expanding, an idea so controversial even Einstein initially dismissed it, threatened to derail his reputation. These pioneers weren't just studying the stars, they were fighting an uphill battle against the scientific establishment, armed with nothing but data and defiance. What's striking isn't just what they discovered, but how they thought. They didn't accept the limits of their tools or the boundaries of accepted theory. When their telescopes showed gaps, they didn't assume emptiness, they assumed ignorance. That shift in perspective from "we see everything" to "we're barely scratching the surface" set the stage for every cosmic mystery that followed. Without their willingness to stand at the edge of the unknown and demand answers, we might still believe the universe was static, small, and simple. Instead, they handed us a map with vast blank spaces, not as a dead end, but as an invitation. The message was clear: the real discoveries lie in what we can't yet see. The Michelson-Morley experiment wasn't just another test, it was a gamble that shook the foundations of physics. Picture two scientists, Albert Michelson and Edward Morley, in a basement lab in Cleveland in the late 1800s, convinced they could measure the invisible fabric of the universe. At the time, everyone believed space was filled with a mysterious substance called the ether, an unseen medium through which light waves traveled, like sound through air. If the ether existed, Earth's movement through it should create a detectable ether wind, subtly altering the speed of light depending on direction. Michelson and Morley built an ingenious device, an interferometer, so sensitive it could measure shifts smaller than a fraction of a wavelength of light. They expected to catch the universe in motion to prove the ether was real, but when they turned their instrument toward the sky, the result was nothing. No shift, no wind, no ether. At first, this seemed like a disaster. How could their careful measurements show no effect? Some scientists dismissed it as a flaw in the experiment, but Michelson and Morley knew their work was sound. That nothing was telling them something radical. The ether didn't exist. Light didn't need a medium to travel through. It moved at a constant speed, no matter how fast or in what direction you were moving. This wasn't just a minor correction, it was a direct challenge to Newtonian physics, the bedrock of science for centuries. The implications were staggering. If there was no ether, how did light behave? What did that mean for time and space? Enter a young patent clerk named Albert Einstein. A decade later, he took Michelson and Morley's baffling result and turned it into a revolution. His theory of special relativity declared that the speed of light was constant for all observers, regardless of their motion. Time and space weren't fixed. They stretched and warped to keep light's speed unchanging. The failure of the Michelson-Morley experiment became the cornerstone of modern physics, proving that the most profound discoveries often come from the absence of what we expect to find. What's remarkable isn't just the experiment's outcome, but the courage it took to accept it. Michelson and Morley could have dismissed their own results, tweaked their data to fit the prevailing theory. Instead, they let the silence speak. In science, as in life, it's easy to cling to what we think we know, but progress happens when we dare to stare into the void and admit we were wrong. That humility, the willingness to let nothing rewrite everything, is what separates a good scientist from a revolutionary. The Michelson-Morley experiment didn't just measure empty space. It measured the limits of human imagination, and in doing so, pushed them further than anyone thought possible. Vera Rubin didn't set out to rewrite astronomy. She just wanted to understand why galaxies weren't behaving the way they should. In the 1970s, while studying the rotation of spiral galaxies, she noticed something strange. The stars at the edges were moving just as fast as those near the center, defying Newton's laws. According to physics, those outer stars should have been slowing down like planets farther from the sun. But Rubin's data showed no such drop-off. The only explanation, something invisible, something massive, was exerting an extra gravitational pull. That something was dark matter, a mysterious substance that doesn't emit, absorb, or reflect light. It was everywhere, shaping the cosmos, yet completely hidden from view. Rubin's discovery was met with resistance. Many scientists dismissed her findings, insisting she must have made a mistake. After all, how could the majority of the universe's matter be utterly invisible? But Rubin persisted, meticulously collecting data from hundreds of galaxies. Each observation told the same story. The stars were moving too fast, and the only way to explain it was to accept that we were missing most of the picture. Her work forced astronomy to confront an uncomfortable truth. We'd been studying the universe with blinders on, mistaking the visible for the whole. Today, dark matter remains one of science's greatest puzzles. We still don't know what it's made of, only that its gravitational fingerprints are everywhere. From the way galaxies cluster together to the bending of light around massive objects, its influence is undeniable. Modern experiments like the Large Hadron Collider and underground detectors filled with liquid xenon are hunting for dark matter particles, hoping to catch a fleeting interaction. Yet after decades of searching, the substance remains elusive, a cosmic ghost that refuses to reveal itself. What's fascinating isn't just the mystery itself, but how it mirrors the struggles of earlier astronomers. Like Michelson and Morley measuring the absent ether, or Hubble charting the expansion of space, Rubin's work proves that progress often begins with a discrepancy, a whisper of "this doesn't add up." The history of astronomy is littered with moments where scientists stared at their data, scratched their heads, and realized they were asking the wrong questions. Dark matter is the latest chapter in that story, a reminder that the universe is under no obligation to make sense to us, and perhaps that's the most humbling lesson of all. Every time we think we've mapped the cosmos, it reveals another layer of complexity. The invisible outweighs the visible by 5 to 1, meaning everything we've ever seen, every star, every planet, every galaxy, is just the tip of the iceberg. Dark matter isn't an anomaly, it's the norm. It's the scaffolding holding the universe together, the silent architect of the cosmic web. Rubin once said, "We don't know what most of the universe is made of." That's a remarkable statement. She wasn't just talking about dark matter. She was pointing to the heart of science itself, the courage to admit ignorance, to chase the unknown, and to measure the immeasurable. Because sometimes the most profound truths aren't found in what we observe, but in the gaps between. The story of dark matter isn't finished. It's an open invitation, a challenge to future generations. Keep looking, keep questioning, and never assume that nothing means nothing. After all, the universe's greatest secrets are hiding in plain sight, or more accurately, in plain darkness. Sometimes the most revolutionary discoveries begin with annoyance. That's exactly how it was for Arno Penziers and Robert Wilson in 1964, when they pointed their radio telescope at the sky and picked up a persistent hiss, an irritating background noise that wouldn't go away. At first, they assumed it was interference. Maybe it was pigeon droppings on their antenna or static from nearby New York City. They scrubbed the equipment, shooed away the birds, even dismantled and rebuilt their receiver. But the noise remained, a faint whisper coming from every direction, day and night. What they didn't realize was that they'd stumbled onto the oldest signal in the universe, the cosmic microwave background, the cooled remnants of the Big Bang's fiery birth. This wasn't just random static. It was a snapshot of the cosmos when it was just 380,000 years old, a time when the universe had cooled enough for light to break free from the dense plasma of its infancy. That faint glow, now stretched into microwaves by the expansion of space, was the echo of creation itself. But when Penziers and Wilson first published their findings, the reaction was mixed. Some scientists were skeptical. After all, how could a uniform hum of radiation, barely warmer than absolute zero, be evidence of something as dramatic as the universe's explosive beginning? The answer lay in a theory that had been dismissed for decades, the Big Bang. In the 1940s, physicist George Gamow had proposed that if the universe began in a hot, dense state, it should have left behind a faint afterglow. But without proof, the idea languished. Then, in a beautiful twist of fate, Penziers and Wilson's problem turned out to be the missing piece. Their accidental discovery matched Gamow's predictions perfectly, delivering the smoking gun for the Big Bang theory. Suddenly, that annoying hiss became the Rosetta Stone of cosmology, a message from the universe's first moments. What's astonishing isn't just the discovery, but how it reshaped our place in the cosmos. The cosmic microwave background isn't just radiation, it's a time machine. By mapping its tiny fluctuations, scientists have reconstructed the infant universe's structure, revealing the seeds of galaxies and the precise geometry of space itself. Satellites like COBE, WMAP, and Planck have turned that faint whisper into a high-definition portrait, showing us wrinkles in spacetime that predate stars, planets, even atoms. Yet the real lesson here isn't about technology, it's about perspective. Penziers and Wilson weren't looking for the Big Bang, they were just trying to eliminate noise. But their willingness to chase down an anomaly, to treat nothing as a clue rather than a nuisance changed everything. Science thrives on these moments when curiosity turns frustration into revelation. The cosmic microwave background reminds us that the universe speaks in riddles, and sometimes the answers aren't in the signals we seek, but in the static we ignore. Today, that faint glow is the foundation of modern cosmology, a cornerstone as vital as Hubble's expanding universe or Rubin's dark matter. It's proof that even in emptiness there's a story, one written in the cold, quiet aftermath of the universe's first light. And like all great discoveries, it started with a simple question. Why won't this noise go away? The answer, of course, was far grander than anyone imagined. Sometimes to measure nothing is to find everything. Failure is a word that makes most scientists flinch, but in astronomy, it's often the first step towards something extraordinary. For every groundbreaking discovery like the cosmic microwave background or dark matter, there are dozens of experiments that seem to go nowhere. Instruments return static instead of signals, telescopes capture blank patches of sky, and meticulous calculations lead to dead ends. Yet these so-called failures aren't just setbacks, they're guideposts, steering us away from false assumptions and toward deeper truths. Take the case of the missing mass problem in galaxy clusters. In the 1930s, astronomer Fritz Zwicky noticed that galaxies within the Coma cluster were moving so fast they should have flown apart. He proposed the existence of unseen matter holding them together, a radical idea at the time. But without the tools to prove it, his theory was largely ignored for decades. It wasn't until Vera Rubin's work in the 70s that the scientific community took dark matter seriously. Zwicky's failed hypothesis wasn't wrong, it was simply ahead of its time. His persistence in the face of skepticism laid the groundwork for one of cosmology's biggest revelations. Then there are the experiments that don't just fail, they defy expectations entirely. In the late 1990s, two teams studying distant supernova expected to find the universe's expansion slowing down due to gravity. Instead, their data showed the opposite. The expansion was accelerating, driven by an unknown force now called dark energy. This wasn't just a null result, it was a cosmic curveball that upended everything. The teams could have dismissed their findings as errors, but they leaned into the uncertainty, and in doing so, uncovered a mystery that still puzzles physicists today. What these stories reveal is that science doesn't progress in straight lines. Every dead end forces us to ask better questions. When the Laser Interferometer Gravitational Wave Observatory first turned on, it spent years detecting nothing but seismic noise and passing trucks. Critics called it a costly mistake until one day in 2015, when it captured the faint ripple of two black holes colliding a billion light-years away. That single signal, buried in years of failure, opened an entirely new window on the universe. The real courage in science isn't just celebrating breakthroughs, it's embracing the messy, uncertain process that leads to them. Astronomers don't just study the stars, they wrestle with ambiguity, spend nights debugging equipment, and face the humbling reality that the universe owes them no answers. But that's where the magic happens. Every null result, every unexpected silence is a reminder that we're still learning how to listen. And sometimes the most profound discoveries begin with admitting we don't know and then daring to find out. There's a quiet despair that comes with staring into the void and seeing nothing, not because there's nothing to find, but because no one else believes you. For astronomers chasing the invisible, the greatest challenge isn't technical, it's psychological. Imagine spending years, even decades, collecting data that defies explanation, only to have your peers dismiss it as error or fantasy. The weight of that isolation can crush even the most determined minds. Take Fritz Zwicky, who first proposed dark matter in the 1930s. His colleagues called him eccentric, even arrogant, for insisting galaxies were held together by unseen mass. He famously nicknamed them spherical bastards, not just out of frustration, but as a defense against the loneliness of being the only one who saw the truth. The scientific method is built on skepticism, but when that skepticism turns into dismissal, it becomes a wall. Vera Rubin faced this when she presented her findings on galaxy rotation. Male colleagues would interrupt her lectures, questioning her methods, even suggesting she'd misread her own data. One critic told her outright, "You're wrong because I know what the answer should be." For years, she worked in near silence, her breakthroughs met with indifference. The toll wasn't just professional, it was personal. Late nights at the telescope meant missed birthdays, strained relationships, and the gnawing fear that her life's work might never be recognized. Then there's the doubt that creeps in when the universe refuses to cooperate. Penziers and Wilson spent months convinced their cosmic microwave background signal was pigeon interference. The longer the mystery persisted, the more they questioned their own sanity. Science celebrates eureka moments, but rarely the anguish that precedes them, the sleepless nights staring at data that makes no sense, the terror of realizing you might have wasted your career chasing a ghost. The backlash can be brutal. When the teams studying dark energy first announced the universe's expansion was accelerating, some physicists accused them of statistical cherry-picking. One Nobel laureate publicly called their conclusions premature. forcing them to revisit every calculation, every assumption under a microscope of scrutiny. For young researchers, this kind of rejection can be career-ending. Funding dries up, conferences stop inviting you, and the academic whispers begin. Maybe they're just not cut out for this. Yet these stories aren't just about struggle, they're about stubbornness. The refusal to let go of an idea, even when the world says you should. Zwicky kept publishing papers on dark matter long after his peers stopped reading. Rubin mentored young women in science, building a legacy despite the barriers. Penziers and Wilson didn't discard their hiss, they followed it to the edge of human understanding. What drives someone to keep searching when every sign says, turn back? Perhaps it's the same force that pushes explorers to scale impossible mountains or artists to rewrite the rules of their craft. There's a moment deep in the frustration when curiosity becomes something fiercer, an almost irrational conviction that the answer is worth any cost. Astronomers don't measure nothing because it's easy, they do it because they can't not. The night sky becomes a mirror, reflecting back not just the universe's mysteries, but their own determination to solve them. And that's the hidden lesson in these battles. Science isn't just a collection of facts, it's a human endeavor, messy and emotional. Every paradigm shift begins with someone willing to stand alone, to weather the storms of doubt, and to trust in the silence when no one else will. The next time you look up at the stars, remember, behind every discovery are the scars of those who dared to ask, what if, and refused to look away. Science has always had an uneasy relationship with the unknown, especially when that unknown looks like nothing at all. To the public, and even to many researchers, experiments that chase the invisible can seem like exercises in futility. Why pour resources into measuring emptiness when there are so many tangible mysteries to solve? The skepticism is understandable, but history keeps proving it wrong. Time and again, the moments we dismiss as dead ends turn out to be the hinges of revolution. Consider how the Michelson-Morley experiment was initially received. When their search for the ether came up empty, some colleagues shrugged it off as a technical fluke. The idea that their failed experiment might rewrite physics seemed absurd until Einstein showed it had. Decades later, Vera Rubin faced similar disbelief. Her charts of galaxy rotations were met with shrugs. Invisible matter sounded like science fiction, not serious research. Even Penziers and Wilson's cosmic static was nearly written off as equipment noise. The pattern is clear. Breakthroughs born from nothing must first survive the gauntlet of dismissal. Changing this perception isn't just about data, it's about storytelling. Scientists like Carl Sagan and Neil deGrasse Tyson didn't just present facts, they framed the unknown as an adventure. When Rubin described dark matter, she didn't just cite numbers, she painted a picture of the universe as a grand detective story, with most of the clues still hidden. That shift in narrative matters. The public tolerates uncertainty when it feels like exploration, not confusion. Yet the burden shouldn't fall solely on researchers. Institutions play a role too. Peer review panels often favor safe projects with predictable outcomes over high-risk, high-reward pursuits. Funding bodies hesitate to back studies that might yield nothing. This creates a perverse incentive. The very experiments most likely to upend our understanding are the least likely to get funded. Some fields, like particle physics, have started embracing null result journals, recognizing that knowing what isn't there can be as valuable as knowing what is. The irony is that society celebrates these discoveries once they're validated. Dark matter now fuels blockbuster movies. The Big Bang is dinner table conversation. But the messy, uncertain path to those truths remains misunderstood. We love the eureka moment but forget the years of lonely skepticism that preceded it. Maybe that's the real lesson here. Science isn't just a collection of answers. It's a discipline brave enough to keep questioning, even when the only reply is silence. And sometimes that silence speaks volumes. Securing funding for experiments that might come up empty is one of the most frustrating hurdles in science, especially when those failures could rewrite textbooks. Grant committees want certainty, measurable outcomes, and clear deliverables. But what happens when the most important question you can ask is also the riskiest? Imagine pitching an idea to study an invisible force or measure the absence of a phenomenon that might not even exist. To a room full of budget-conscious administrators, it sounds less like science and more like a gamble. This bias toward safe research isn't just bureaucratic caution, it's a systemic blind spot. Consider the hunt for gravitational waves. For decades, the idea of detecting ripples in spacetime seemed like science fiction. Building LIGO, the Laser Interferometer Gravitational Wave Observatory, required hundreds of millions of dollars and years of work with no guarantee of success. Critics called it a boondoggle, a colossal waste of resources chasing a signal that might never appear. Even within the scientific community, skeptics argued the technology wasn't sensitive enough, the universe too quiet. Yet the team persisted, cobbling together funding from reluctant agencies and private donors who believed in the long shot. When LIGO finally detected gravitational waves in 2015, the discovery didn't just validate Einstein, it opened an entirely new way to observe the cosmos. The irony is that some of history's most transformative discoveries came from projects initially deemed too speculative. Take the Keck Observatory in Hawaii, where astronomers fought for years to secure funding for larger telescopes. Detailing the chemical composition of distant stars sounded like niche research at the time, but those observations later revealed the first exoplanets. The same pattern repeats. Vera Rubin's dark matter work was initially dismissed as a fringe pursuit, while studies of cosmic inflation, the theory that the universe expanded exponentially in its first moments, were once considered untestable. Today, these ideas form the bedrock of modern cosmology. So why does funding remain so skewed toward low-risk projects? Part of it comes down to how science is evaluated. Grant applications often prioritize broader impacts and immediate applications, leaving pure curiosity-driven research at a disadvantage. A proposal to map the cosmic microwave background might struggle to explain its real-world benefits, while a study on solar cell efficiency checks obvious boxes. This creates a perverse incentive. Scientists must frame their work in ways that sound practical, even if the most revolutionary insights come from embracing the unknown. Yet there are glimmers of change. Organizations like the Breakthrough Prize and the Templeton Foundation now explicitly fund high-risk, high-reward science. Some universities have created blue-sky grants for projects with no guaranteed outcome, recognizing that true innovation often starts with a question, not a hypothesis. And in a quiet revolution, a handful of journals have begun publishing Null results, studies that didn't find what they expected because even failure can steer the entire field in the right direction. The astronomers who push forward despite these obstacles aren't just stubborn, they're custodians of a deeper truth. Science isn't just about answering questions, it's about asking the right ones, even when the path is uncertain. Every time a researcher chooses curiosity over convenience, they're betting on a future they can't yet see. And as history shows, those bets have a way of paying off in ways no one could predict. After all, the universe doesn't keep its secrets in the places we've already looked. Measuring the invisible isn't just about brilliant ideas, it's a battle against the limits of our tools. For centuries, astronomers have been trapped in a frustrating paradox. The universe whispers its secrets, but our instruments are too crude to hear them. Take the hunt for gravitational waves. The idea that colliding black holes could ripple spacetime was proposed decades before we had machines sensitive enough to detect such subtle distortions. Early prototypes in the 1960s could barely sense a passing truck, let alone a cosmic event billions of light years away. It took 50 years of painstaking engineering, lasers refined to atomic precision, mirrors suspended in near-perfect vacuum, vibration dampening so advanced it could cancel out the tremors of ocean waves before LIGO finally caught that first fleeting signal. The delay wasn't due to lack of imagination. The technology simply hadn't caught up to the theory. This gap between concept and capability defines much of astronomy's history. Vera Rubin's dark matter discoveries relied on spectrographs precise enough to measure the faint Doppler shifts of distant stars' instruments that didn't exist when Fritz Zwicky first proposed the idea. Even Hubble's groundbreaking revelation about Andromeda hinged on Henrietta Leavitt's work with photographic plates, a technology that replaced hand-drawn star charts and finally allowed scientists to quantify stellar brightness with consistency. Every leap forward in cosmic understanding has been shadowed by the same reality. We can only see as far as our tools let us. Sometimes the limitations aren't just technical, they're physical. The cosmic microwave background, that faint echo of the Big Bang, had been bathing the universe for 14 billion years before Penziers and Wilson stumbled upon it. But detecting its faint glow required more than luck. It needed a radio telescope free from interference, and even then, the signal was barely distinguishable from noise. Modern satellites like Planck have since mapped its variations in exquisite detail, but only by operating at temperatures near absolute zero, where even the faintest heat wouldn't drown out the universe's oldest light. What's remarkable isn't just the patience required to bridge these gaps, but the foresight. Scientists like Rainer Weiss, who envisioned LIGO in the 1970s, knew the technology of their time was hopelessly inadequate. Instead of abandoning the quest, they mapped out the incremental steps needed to make detection possible, a roadmap spanning generations. Similarly, today's researchers planning telescopes like the James Webb successor or next-generation neutrino detectors aren't just building for now. They're planting trees whose fruit they may never live to see. This long-game mentality runs counter to our modern obsession with instant results. In an era of rapid tech turnover, astronomy demands the opposite: decades of refinement for instruments that may only capture a few seconds of usable data. The Event Horizon Telescope, which produced the first image of a black hole in 2019, required synchronizing observatories across continents with atomic clock precision, a feat that took 20 years of trial and error. Each failure wasn't a setback but a lesson, each dead end a signpost pointing toward better solutions. Perhaps that's the most humbling lesson of all. The universe doesn't adjust its mysteries to fit our tools. Dark matter won't suddenly glow because our telescopes improve. Gravitational waves won't grow louder for convenience. Progress happens when we stubbornly refine our instruments until they're delicate enough to overhear the cosmos' quietest conversations. The history of astronomy isn't just a story of brilliant minds. It's a testament to the craftsmen, engineers, and unsung tinkerers who turned impossible dreams into precision machinery. Because in the end, measuring nothing isn't about absence. It's about preparing to recognize something when it finally, fleetingly appears. Science doesn't exist in a vacuum. Every discovery carries consequences, and sometimes the quest to measure nothing forces astronomers to confront uncomfortable ethical choices. Take the case of neutrino detectors, massive installations buried deep underground or submerged in ice. These experiments hunt for ghostly particles that barely interact with matter, requiring vast, sensitive volumes to catch even a handful of signals. But building them often means disrupting fragile ecosystems, drilling into Antarctic ice sheets, or flooding abandoned mines with ultra-pure water. The irony is stark. To study the universe's most elusive particles, we must alter the very environments we strive to protect. Then there's the specter of dual-use technology. Radio telescopes designed to listen for cosmic whispers can also be repurposed for military surveillance. The algorithms developed to filter noise from gravitational wave data could, in theory, enhance missile tracking systems. Even something as seemingly benign as dark matter research, if it ever yielded practical applications, might unlock energies dwarfing nuclear power with all the attendant risks. Astronomers rarely set out to enable harm, but history shows that pure knowledge has a way of spilling beyond its original intent. The same quantum mechanics that explained the atom gave us the atomic bomb. Funding priorities add another layer of tension. In a world facing climate crises and inequality, how do we justify billions spent chasing invisible particles or mapping the cosmic microwave background? Critics argue these projects divert resources from urgent earthly problems, creating a moral asymmetry. We probe the depths of space while ignoring suffering down here. Defenders counter that curiosity-driven science has, time and again, yielded unexpected benefits. GPS, medical imaging, even the internet itself grew from seemingly abstract research. But that's cold comfort to communities watching telescopes rise while their schools crumble. Perhaps the thorniest dilemma lies in the act of looking itself. Some indigenous cultures view certain celestial phenomena as sacred, their stories woven into the stars. When astronomers declare these same stars data or propose constructing observatories on sacred lands, it sparks clashes between worldviews. The 30-meter telescope's planned construction on Mauna Kea, Hawaii, became a flashpoint not just over environmental concerns, but over who gets to define the sky's meaning. Science prizes objectivity, but the sky has never been neutral. It's a mirror reflecting our values back at us. Navigating these conflicts requires more than equations. It demands humility. The astronomers who pause to consult with indigenous elders or who redesign experiments to minimize environmental harm aren't abandoning rigor, they're expanding it. Ethics, like the universe, is full of unknowns. Just as measuring cosmic silence teaches us about what's missing, wrestling with these dilemmas reveals the gaps in our own assumptions. The greatest discoveries aren't just about what we find, but how we choose to look. And sometimes the most responsible thing an astronomer can do is ask not, can we measure this? But should we? The most profound discoveries in astronomy rarely belong to a single name etched in textbooks. They're the result of countless hands, minds, and even rival institutions working toward a common goal. Consider the Event Horizon Telescope's first image of a black hole, an achievement that required synchronizing 8 observatories across 4 continents, with teams from 20 countries sharing data in real time. No single researcher could have pulled that off, no matter how brilliant. Yet this level of collaboration exists in tension with academia's cutthroat reality, where tenure battles, funding shortages, and the race to publish first can turn colleagues into competitors. The astronomers who navigate this paradox best understand something crucial. Measuring the invisible isn't just about technology, it's about trust. Take the delicate dance between the teams hunting for dark matter. Underground labs in Italy, South Dakota, and South Korea compete to be the first to detect a hypothetical particle, yet their scientists routinely share calibration techniques and noise reduction strategies. They know that proving dark matter exists is bigger than any one experiment. Similarly, when LIGO detected gravitational waves, the discovery paper listed over 1,000 co-authors, a testament to the decades of cross-generational effort required to hear the universe's faintest ripples. These projects thrive on a radical openness where data is scrutinized by rivals and mistakes are caught faster because egos take a backseat to accuracy. But this idealism bumps against harsh incentives. Academic promotions often hinge on being the sole name atop a groundbreaking paper, not the 50th collaborator. Funding agencies reward flashy headlines over incremental teamwork. The result, researchers sometimes hoard data, delay publishing to perfect results, or even sabotage peer reviews. Vera Rubin once recounted how a colleague withheld critical spectral data for years, slowing dark matter research until he retired and his notebooks were finally opened. The cost of such secrecy isn't just personal, it's cosmic. Every month lost to competition is a month the universe's secrets stay hidden. What's fascinating is how the field self-corrects. Astronomy's greatest leaps often come from unlikely alliances. When Penziers and Wilson couldn't explain their mysterious radio hiss, they reached out to rival physicists at Princeton who'd predicted the cosmic microwave background but lacked the tools to detect it. That partnership turned frustration into Nobel-worthy insight. Today, projects like the James Webb Space Telescope enforce strict collaboration clauses, requiring scientists to release findings quickly for collective analysis. Even patent disputes are rare. You can't own the laws of physics, only the privilege of uncovering them. The lesson here isn't that competition is bad, it drives innovation, but that measuring nothing demands a special kind of generosity. When your experiment might spend years yielding silence, you need peers who'll double-check your work, not dismiss it. When your telescope catches a glitch instead of a galaxy, you need rivals willing to say, "We hit that dead end too, here's how we pivoted." The astronomers who leave lasting legacies aren't just the ones with the sharpest minds, but those who build ladders for others to climb. Because the universe doesn't care who gets credit, only that someone keeps looking. There's a number that's been haunting astronomers for decades, a single value that holds the key to understanding how fast the universe is expanding. It's called the Hubble constant, and it should be straightforward. Measure how quickly galaxies are moving away from us, factor in their distances, and voila, you've got your answer. But here's the catch: depending on how you measure it, you get wildly different results, and no one can figure out why. This isn't just a minor discrepancy, it's a full-blown crisis in cosmology, one that's forcing scientists to confront the possibility that they've either made a colossal mistake or stumbled onto something entirely new about the fabric of reality. Let's break it down. One way to calculate the Hubble constant is by studying nearby galaxies, using pulsating stars called Cepheid variables as cosmic yardsticks. This method, refined over a century since Henrietta Leavitt first unlocked their secrets, gives us one number. Another approach looks at the afterglow of the Big Bang, the cosmic microwave background, and extrapolates forward using our best models of the universe's evolution. That gives us a different number, and here's the kicker. These results disagree by about 10%, a gap that might seem small until you realize it's the difference between a universe that's 13.8 billion years old and one that's significantly younger or older. The tension between these measurements isn't just a technical glitch, it's a symptom of something deeper. Imagine trying to bake a cake where the recipe calls for 2 cups of flour, but every time you measure it, the scale gives you a different amount. You'd start questioning the scale, the flour, even the laws of gravity. That's where cosmologists are right now. Some think the problem lies with our measurements. Maybe Cepheid variables aren't as reliable as we thought, or perhaps there's hidden dust skewing the cosmic microwave background. Others suspect the models themselves are flawed, that we're missing a fundamental ingredient in our understanding of dark energy, gravity, or even the very nature of spacetime. The stakes couldn't be higher. If the discrepancy is real, if the universe truly is expanding faster than our theories predict, it could mean there's an undiscovered force at work, a particle or field that's been hiding in plain sight. Some have proposed early dark energy, a mysterious push that might have existed in the universe's infancy, subtly altering its expansion history. Others speculate about modifications to Einstein's theory of gravity, tweaking the equations that have governed cosmology for a century. These aren't small adjustments, they're potential revolutions, ideas that could rewrite physics as we know it. What's fascinating isn't just the science, it's the human drama behind it. Teams of astronomers have spent years cross-checking their data, hunting for errors, even reanalyzing decades-old observations. The debates can get heated, with papers flying back and forth, each side convinced the other has missed something obvious. Yet beneath the rivalry lies a shared awe. However this plays out, one thing is certain: the universe is trying to tell us something, and we're only just beginning to listen. This isn't the first time astronomy has faced a crisis like this. The history of science is littered with moments where a stubborn discrepancy led to something extraordinary. The misaligned orbit of Mercury hinted at general relativity. The missing energy in beta decay revealed the neutrino. The Hubble constant tension might be the latest chapter in that story, a clue wrapped in a paradox waiting for someone to unravel it. Until then, astronomers will keep measuring, debating, and staring into the void, knowing that sometimes the most important answers come from the questions we can't yet solve. Serendipity might seem like an odd word to associate with science after all. Isn't discovery supposed to be methodical, deliberate? But some of astronomy's most transformative moments have come not from meticulous planning, but from pure, unscripted chance. Take the case of Jocelyn Bell Burnell, a graduate student in 1967 who noticed an odd blip in her radio telescope data, a rhythmic pulse so precise it seemed almost artificial. At first, she and her advisor jokingly labeled it LGM1, short for Little Green Men, wondering if they'd stumbled onto an alien signal. But what they'd actually found was the first pulsar, a rapidly spinning neutron star emitting beams of radiation like a cosmic lighthouse. Bell Burnell wasn't looking for pulsars, she was mapping radio waves from distant quasars, yet her willingness to chase down that anomaly, to treat nothing as a clue, rewrote our understanding of stellar evolution. Then there's the story of quasars themselves. In the 1950s, astronomers scanning the skies for radio sources kept finding mysterious, star-like objects that defied classification. Their light spectra made no sense, unlike anything seen before. Some researchers dismissed them as instrument errors or local interference. But Martin Schmidt, peering at one particularly puzzling object called 3C273, realized its light was redshifted so dramatically that it had to be billions of light years away, shining with the brightness of 100 galaxies. The term quasar was coined soon after, revealing a new class of unimaginably powerful objects fueled by supermassive black holes. Like Bell Burnell, Schmidt wasn't hunting for quasars, he was just following the trail of an anomaly others had ignored. These stories aren't exceptions, they're part of a pattern. The cosmic microwave background, dark energy, even the rings of Uranus were all stumbled upon while scientists were looking for something else. But here's the crucial detail: serendipity alone isn't enough. Luck favors the prepared mind, as Louis Pasteur famously said. Penziers and Wilson only recognized their radio hiss as cosmic because they'd exhaustively ruled out every earthly explanation. Bell Burnell spotted her pulsar because she'd spent months learning every quirk of her telescope, so she knew when something didn't belong. The real magic happens at the intersection of curiosity and rigor. When an astronomer peers at a blip on a screen and thinks, "That's odd," instead of "That's noise," the universe has a way of rewarding that attention. It's as if the cosmos reserves its deepest secrets for those willing to listen beyond their original questions. And that's the paradox of scientific discovery. Sometimes the most profound truths emerge not from the answers we seek, but from the detours we didn't plan to take. So the next time you hear about a breakthrough born from accident, remember, it wasn't just luck. It was the result of countless hours of preparation, a mind trained to recognize significance in the seemingly insignificant. Because in the end, the universe doesn't reveal its mysteries on demand. It whispers them in the static, hides them in the margins, and waits for someone perceptive enough to notice. And when they do, the whole story changes. At the heart of every great scientific mystery lies a paradox, and measuring nothing might be the ultimate one. Think about it. How do you define emptiness in a cosmos where even the darkest voids hum with quantum fluctuations, where so-called empty space teems with virtual particles popping in and out of existence? This isn't just a technical challenge. It's a window into how we perceive reality itself. For centuries, philosophers and scientists have grappled with the nature of absence. From Aristotle's horror vacui, the idea that nature abhors a vacuum, to the Zen Buddhist concept of mu, the fertile void from which all potential springs. What we call nothing is never truly empty. It's a canvas waiting to be reinterpreted. Consider the way language shapes our understanding. When astronomers talk about the vacuum of space, they don't mean true nothingness. They mean the absence of matter, a distinction that hides layers of complexity. Even in the emptiest regions between galaxies, there's still gravitational curvature, dark energy, and the faint glow of the cosmic microwave background. Our instruments might register silence, but that silence is full of information. It's like listening to a recording of a quiet room. What sounds like blank tape to the untrained ear could reveal subtle echoes, background hums, or the distant murmur of traffic to someone who knows how to listen. This blurry boundary between presence and absence forces us to confront uncomfortable questions. If dark matter and dark energy make up 95% of the universe's content, does that mean the atoms we're made of, the stars, planets, and everything we can see are just cosmic afterthoughts? The unsettling answer might be yes. Our entire visible universe could be a mere froth on an invisible ocean, a glitch in the fabric of something far stranger. This inversion of perspective, where the real world becomes the exception rather than the rule, echoes through history, from Plato's cave to modern quantum field theory, reminding us that reality is often not what it seems. The act of measuring nothing also exposes the limits of human perception. Our brains evolved to notice objects, edges, and movement, not the spaces between them. Try staring at the blank sky between stars. Your eyes will instinctively dart to the pinpricks of light, not the darkness. This bias toward positive signals runs deep in science too. For decades, astronomers dismissed anomalies like Vera Rubin's galaxy rotations or Penziers and Wilson's radio hiss as noise, simply because they didn't fit the expected patterns. It takes a special kind of discipline to train yourself to value absence as much as presence, to treat silence as data rather than disappointment. Perhaps that's why these discoveries feel so profound. They don't just add to our knowledge, they redefine the framework of what knowledge is. Every time we measure nothing and find something, whether it's the ether's absence birthing relativity or dark matter's invisibility reshaping cosmology, we're forced to recalibrate our place in the cosmos. The universe isn't just stranger than we imagine, it's stranger than we can imagine. And in that gap between what we see and what's really there, in the quiet spaces where our assumptions fall apart, lies the most exciting frontier of all, the uncharted territory of what we don't yet know we don't know. The future of measuring nothing isn't about better tools, it's about redefining what nothing even means. Right now, the James Webb Space Telescope is peering deeper into cosmic history than ever before, but it's not just capturing stunning images of distant galaxies. Its infrared eyes are tuned to the gaps, the dark spaces between stars where ancient light has stretched into near nothingness. Every faint photon it collects from these voids could rewrite our understanding of the early universe's structure. Meanwhile, deep underground, experiments like LUX Zeppelin and Darwin are waiting for dark matter particles to bump into ultra-pure liquid xenon, turning an absence of noise into potential proof of invisible mass. These aren't just upgrades to old methods, they're entirely new languages for listening to the universe's silence. What makes this next era so exciting is how it turns limitations into opportunities. Take quantum sensors, which exploit the bizarre rules of the subatomic world to detect impossibly weak signals. Future versions could measure gravitational waves so faint they'd make LIGO detections look like earthquakes. Or consider neutrino observatories like IceCube, where scientists watch for flashes of light caused by particles that pass through entire planets without interacting. These detectors don't just push boundaries, they operate in realms where traditional physics breaks down, hunting for phenomena we can't yet describe. It's like trying to study shadows cast by objects that haven't been invented yet. The real revolution, though, might come from combining these approaches. Imagine linking gravitational wave detectors with neutrino telescopes and next-generation radio arrays into one interconnected web. A black hole merger spotted by LIGO could trigger IceCube to search for accompanying neutrinos while the Vera see. Rubin Observatory's optical scans pinpoint the location. This multi-messenger astronomy turns the cosmos into a symphony where we're learning to hear every instrument, even the ones playing in frequencies we once thought were silent. Yet the greatest discoveries may lurk in the data we currently discard. Machine learning algorithms are now sifting through years of failed experiments, searching for patterns too subtle for human eyes. Already, these AI detectives have found pulsars missed by traditional searches and anomalous cosmic rays that defy explanation. As these tools grow more sophisticated, they could uncover entirely new classes of phenomena hidden in plain sight. The astronomical equivalent of realizing your empty attic has been storing priceless artifacts all along. What unites these efforts is a shift in perspective. The astronomers of tomorrow won't just be better equipped, they'll be fundamentally differently minded. Where past generations saw noise, they'll see potential signals. Where others hit dead ends, they'll recognize undiscovered countries. And when their instruments inevitably return baffling null results, they'll smile because history shows that's when things get interesting. The universe's greatest truths have always been hiding in the last places we thought to look. So while we can't predict what they'll find, we know this much: the future of nothing has never looked so full of possibilities. Lessons from these cosmic pioneers reveal a truth both humbling and exhilarating. Science advances not despite uncertainty, but because of it. Consider how Henrietta Leavitt spent years measuring the flickers of variable stars without knowing her work would become the foundation for measuring the universe's expansion. Or how Vera Rubin meticulously charted galaxy rotations while colleagues dismissed her findings, only for dark matter to later redefine cosmology. Their breakthroughs didn't emerge from flawless certainty. They came from staring into the unknown and refusing to blink. This legacy of embracing the unresolved continues today in projects like the Event Horizon Telescope, where teams spent decades sinking observatories across continents without knowing if they'd ever capture a black hole's shadow. The first grainy image of M87's Event Horizon wasn't just a technical triumph. It was a victory for perseverance in the face of overwhelming odds. Similarly, the researchers hunting for actions, hypothetical particles that might explain dark matter, are conducting experiments that could easily yield decades of null results. Yet they press on because history shows that what looks like failure today might be tomorrow's revolution. The beauty of this approach lies in its radical openness. When Michelson and Morley's experiment failed to detect the ether, they didn't discard their results. They let the silence speak. That willingness to follow the evidence wherever it leads, even into uncomfortable territory, separates transformative science from mere data collection. It's why modern astronomers now celebrate negative results, like the recent null detection of certain dark matter candidates, as valuable clues. Each dead end forces us to ask better questions, to refine our theories, and sometimes, like Einstein reimagining spacetime, to rebuild our understanding from the ground up. What these stories teach us isn't just about astronomy, it's a blueprint for curiosity itself. In our daily lives, we're conditioned to seek clear answers and immediate rewards. But the universe operates on a grander scale, revealing its secrets only to those patient enough to sit with ambiguity. The next time you hit a wall in your own pursuits, remember Penziers and Wilson scrubbing pigeon droppings from their antenna, or Fritz Zwicky defending dark matter against decades of ridicule. Progress isn't a straight line, it's a winding path through the unknown, where every wrong turn holds the potential to illuminate something extraordinary. Perhaps that's the most enduring lesson of all. The astronomers who changed our view of the cosmos didn't do so by having all the answers, but by having the courage to live with the questions. Their legacy reminds us that the edge of knowledge isn't a barrier, it's an invitation. And as we stand on the shoulders of these giants, peering into the next great mystery, we do well to embrace the same spirit. Because the universe's greatest truths are still waiting in the silences we've yet to explore. Behind the polished equations and groundbreaking papers, there's a truth we often overlook. Science isn't just about data, it's about people. Real people with sleepless nights, personal struggles, and moments of quiet doubt. Take Edwin Hubble, celebrated for expanding our cosmic horizons, but who spent years haunted by imposter syndrome, convinced he wasn't clever enough for astronomy. Or Jocelyn Bell Burnell, whose pulsar discovery was initially credited to her male advisor, a slight she endured with grace while quietly revolutionizing astrophysics. These aren't just footnotes in history, they're reminders that every leap in understanding comes with a human cost. Consider the emotional toll of chasing the invisible. Vera Rubin's notebooks, filled with meticulous galaxy rotations, also reveal scribbled grocery lists and reminders to pick up her kids, juggling the cosmic and the mundane. Fritz Zwicky, for all his brilliance, grew increasingly isolated as colleagues dismissed his dark matter theories, his frustration leaking into letters where he lamented being surrounded by pygmies. Even Penziers and Wilson, whose cosmic microwave background detection earned them a Nobel, initially feared they'd ruined their careers over what seemed like a technical glitch. The loneliness of being ahead of your time can be crushing, yet there's also joy in these stories, the thrill of connection when someone finally understands. When Henrietta Leavitt's Cepheid variable work enabled Hubble to measure galactic distances, he made sure to credit her despite her being an unpaid computer at Harvard. Decades later, Rubin would mentor young women in astronomy, creating the community she'd lacked. Science at its best isn't a solo endeavor, it's a relay race where each generation lifts the next. What's often missing from textbooks are the small, human moments that change everything. The coffee-stained napkin where a young Einstein scribbled his first thoughts on relativity. The late-night telescope session where Rubin noticed galaxies spinning wrong. a hunch she almost dismissed because it seemed too strange, the way Belle Burnell nearly deleted her pulsar data, thinking it was interference from a passing truck. These aren't just anecdotes, they're proof that discovery doesn't happen in a vacuum. It's messy, emotional, and deeply personal. Perhaps that's the most enduring lesson. The astronomers who reshaped our view of the cosmos weren't infallible geniuses. They were stubborn, curious, and occasionally lucky. They faced rejection, fought for recognition, and sometimes wondered if they were wasting their lives. But they kept looking up, not because they knew they'd find answers, but because the questions themselves were irresistible. In the end, that's what separates a good scientist from a great one. Not just the ability to measure the stars, but the courage to keep searching when the sky seems silent. The story of astronomy isn't just written in the stars. It's etched in the struggles of those who fought to study them against impossible odds. Take Cecilia Payne-Gaposchkin, whose 1925 thesis proposed that stars were made mostly of hydrogen, a radical idea dismissed at the time because it contradicted established wisdom. Not only was she challenging scientific orthodoxy, she was doing it as one of the few women at Harvard College Observatory, where she'd been hired as a computer, a term for underpaid assistants doing tedious calculations. Her work was initially attributed to male colleagues, but her persistence eventually forced the academic world to recognize a truth as fundamental as the composition of the sun itself. Then there's Benjamin Banneker, a self-taught African-American astronomer in the 1700s who predicted solar eclipses and crafted almanacs while enslaved labor built the U.S. Capitol just miles away. With no formal training, he used borrowed books to master celestial mechanics, proving that brilliance isn't confined by circumstance. His letters to Thomas Jefferson challenging racist notions of intellectual inferiority weren't just personal appeals, they were early salvos in a fight for recognition that continues today. These barriers weren't just personal, they shaped the science itself. When Nancy Grace Roman, NAS, a first chief of astronomy, advocated for the Hubble Space Telescope in the 1960s, male colleagues dismissed her as too ambitious. Her relentless lobbying secured funding for what would become humanity's most transformative window on the cosmos, yet for decades, her role was relegated to footnotes. Similarly, Subrahmanyan Chandrasekhar's groundbreaking work on white dwarfs was ridiculed by senior scientists, including Arthur Eddington, who openly mocked his calculations at conferences. Chandrasekhar, an Indian immigrant working in a racially hostile academic environment, waited decades for his Nobel Prize proof that even the most elegant theories can be overshadowed by prejudice. The weight of these struggles wasn't just historical. Take the story of Annie Jump Cannon, who developed the stellar classification system we still use today while working at Harvard for 25 cents an hour, less than her male counterparts. Deaf from middle age, she navigated a world unwilling to accommodate disabilities, yet her hands catalogued hundreds of thousands of stars, laying the groundwork for modern astrophysics. Or consider the indigenous astronomers like Jarita Holbrook, who today bridge Western science with traditional sky knowledge, challenging the field to expand its definition of what counts as astronomy. What's striking isn't just the obstacles these pioneers faced, but how their marginalization shaped their science. Being outsiders gave them a unique lens. Vera Rubin's insistence on studying galaxy rotations, a topic male colleagues dismissed as uninteresting, came from a lifetime of being told her questions didn't matter. Henrietta Leavitt's discovery of Cepheid variables emerged from the meticulous, undervalued work of women assigned to mere data analysis. Their breakthroughs weren't just intellectual, they were acts of defiance, proving that the universe reveals its secrets to those society tries to silence. The echoes of these battles linger. Modern astronomers like Ayamawa Shields, an African-American astrophysicist and classically trained actor, now use storytelling to make science accessible, while projects like the Underrepresented Physicist Scholarship Fund address systemic barriers head-on. The lesson here isn't just about diversity for its own sake. It's about how much we lose when entire perspectives are excluded. Every time a voice is sidelined, we might be missing the next Leavitt, the next Rubin, the next mind capable of seeing what others overlook. Progress isn't inevitable. It's fought for star by star, theory by theory, in observatories and lecture halls where the stakes are as personal as they are profound. The astronomers who broke barriers didn't just expand our knowledge of the cosmos, they expanded our idea of who gets to explore it, and that perhaps is their most enduring discovery. The pursuit of measuring nothing hasn't just reshaped science, it's rewired our collective imagination. Take the iconic moment in Stanley Kubrick's 2001, A Space Odyssey, when the monolith appears, a perfect black rectangle, utterly featureless, yet humming with cosmic significance. That visual wasn't just art, it was a direct nod to humanity's obsession with the invisible, the way we project meaning onto the void. Science fiction has long borrowed from astronomy's most elusive quests, from dark matter fueling interstellar travel in Mass Effect to the cosmic microwave background static inspiring Contact's alien signal. These stories don't just entertain, they translate the anguish and awe of real research into something visceral, letting audiences feel the weight of the unknown. Literature, too, has been haunted by these ideas. Jorge Luis Borges' The Library of Babel imagines a universe as an infinite expanse of books, most filled with gibberish, a metaphor for the cosmic frustration of searching for signal in noise. Meanwhile, Ted Chiang's Story of Your Life, adapted into a rival, wrestles with the limits of human perception, much like astronomers deciphering dark energy's fingerprints. Even children's books like The Dark by Lemony Snicket personify absence as something tangible, teaching young minds that emptiness can be full of mystery. The influence spills into music as well. David Bowie's Space Oddity captures the loneliness of floating in the void, while Radiohead's Subterranean Homesick Alien paints astronomers as misunderstood outsiders. Hip-hop artists like Outkast sample Carl Sagan's Cosmos lectures, weaving cosmic wonder into their beats. These artists aren't just referencing science, they're channeling the emotional core of exploration, the terror and triumph of facing the incomprehensible. Perhaps the most unexpected impact is in gaming. Titles like No Man's Sky and Elite Dangerous turn the vast, mostly empty universe into a playground, where players grapple with the same existential questions as real cosmologists. Why are we here? What's beyond the next star? The game's procedurally generated galaxies, full of uncharted worlds, mirror astronomy's own mapping of the unseen. Even the Destiny franchise builds its lore around the darkness, an enigmatic force that's less evil than simply other, an homage to dark matter's elusive nature. What ties these cultural threads together is their refusal to treat emptiness as passive. Whether it's a filmmaker's black monolith or a poet's negative space, these works insist that absence is alive with potential. They remind us that every time an astronomer points a telescope at nothing, they're not just collecting data, they're continuing a conversation that spans disciplines, centuries, and even species. The next great cosmic revelation might come from a lab, a novel, or the lyrics of a song, because in the end, measuring nothing isn't just science, it's storytelling at the grandest scale. Explaining why scientists spend millions of dollars and countless hours measuring cosmic nothingness isn't just about justifying budgets, it's about igniting wonder. Take the way Neil deGrasse Tyson describes dark matter. Imagine you're in a dark room and suddenly invisible hands start rearranging the furniture. That's what galaxies do under dark matter's influence. By transforming abstract concepts into tangible metaphors, skilled science communicators perform a kind of alchemy, turning the frustration of null results into stories that resonate. When Vera Rubin gave public lectures, she'd hold up a clear glass of water. This looks empty, right, but we know it's teeming with molecules we can't see. Now picture that magnified to galactic scales. Suddenly, the incomprehensible becomes intimate. The challenge lies in overcoming what psychologists call the availability heuristic. Our brains struggle to value what we can't perceive. That's why initiatives like the Dark Matter Day festivals have taken off worldwide, with hands-on exhibits where visitors weigh invisible mass using swinging pendulums or map hidden gravitational fields with laser projections. The most effective outreach doesn't dumb down the science, it repositions absence as detective work. Astronomer Emily Levesque compares it to forensic investigations. You don't need to see the murderer's face to know they were there. The blood spatter tells the story. In cosmology, galaxy rotations are our blood spatter. Digital platforms have revolutionized this storytelling. The James Webb Space Telescope team didn't just release pretty pictures. They created interactive tools letting users slide between infrared and visible light views, revealing how much we miss with human eyes alone. YouTube channels like PBS Space Time build entire episodes around cosmic mysteries, framing null results as cliffhangers rather than dead ends. Even TikTok has become an unlikely ally, with researchers like Sophia Gad-Nasser using viral trends to explain gravitational wave detection through dance moves that mimic interferometer arms. But the real magic happens when scientists admit what they don't know. There's profound power in watching a Nobel laureate say, "We genuinely don't understand why these measurements disagree, and that's exciting." That vulnerability transforms public perception from "scientists have all the answers" to "we're all explorers together." The Atacama Cosmology Telescope project leans into this by live streaming their failures, entire nights where detectors pick up only noise, with commentary explaining why blank screens matter. It's science as reality TV, where the drama isn't in guaranteed success, but in the raw pursuit of understanding. Perhaps the most unexpected allies in this communication challenge are artists. Installations like Rafael Lozano Hemmer's Pulse Spiral, where participants' heartbeats illuminate a galaxy of LEDs proportional to dark matter density, create emotional connections no graph could match. Composer John D. Boswell's Symphony of Science series sets auto-tuned scientist interviews to music, turning cosmic microwave background static into haunting melodies. These collaborations prove that conveying the importance of nothingness requires more than facts. It demands new ways of feeling the universe. At its core, great science communication about measuring the invisible does something radical. It reframes absence as presence. When a child leaves a planetarium show grasping that the empty night sky is actually a treasure map, with dark matter as the dotted lines leading to hidden riches, that's when abstract research becomes personal. Because the ultimate lesson isn't just about astrophysics, it's about learning to see the world differently, to recognize that sometimes what matters most isn't what's there, but our willingness to keep searching for what isn't. There's a profound irony in how the more we learn about the cosmos, the more we realize how little we truly understand. Centuries after Galileo first pointed his telescope skyward, after countless breakthroughs from Hubble to Webb, the universe still guards its deepest secrets with quiet defiance. The astronomers who dedicate their lives to measuring nothing, those who chase dark matter's ghostly fingerprints or pass the silence between gravitational waves, aren't just expanding human knowledge. They're performing a radical act of humility, reminding us that some mysteries may forever hover just beyond our grasp. Consider the fate of the great unification theories, those ambitious attempts to reconcile quantum mechanics with gravity. For decades, brilliant minds like Einstein and Hawking wrestled with equations that might explain everything from the birth of stars to the nature of spacetime itself. Yet the closer we get, the more the universe seems to resist. It's as if we're assembling a jigsaw puzzle only to discover the pieces keep changing shape. This isn't failure, it's the universe teaching us that some questions don't have answers, at least not in forms we can currently comprehend. The history of astronomy is littered with such humbling moments. When Lord Kelvin declared in the 1800s that physics was nearly complete, save for two small clouds on the horizon, those clouds turned out to be relativity and quantum theory upheavals that shattered classical physics. Today's astronomers face their own version of this reckoning. The Hubble tension, the stubborn disagreement over how fast the universe is expanding, isn't just a technical glitch. It's a flashing neon sign pointing to gaps in our understanding, perhaps hinting at entirely new physics waiting to be discovered. What makes this pursuit so extraordinary isn't the certainty of eventual solutions, but the willingness to dwell in uncertainty. The Vera Rubin Observatory, set to begin its legacy survey of space and time, will catalogue billions of galaxies, knowing full well that most of their mass is invisible to its lenses. The scientists behind the upcoming LISA gravitational wave detector acknowledge they might spend years listening to cosmic silence before catching a whisper. This isn't blind optimism, it's a mature recognition that progress often means sitting with discomfort, embracing the not knowing as part of the journey. Perhaps the greatest lesson from these cosmic explorers is that science, at its core, isn't about conquering the unknown, it's about developing a relationship with it. When Jocelyn Bell Burnell first detected pulsars, she didn't just add another entry to astronomy's catalogue, she revealed how much stranger the universe was than anyone had imagined. Every time we measure nothing and find something, we're not closing the book on mystery. We're opening new chapters filled with even deeper questions. This perspective transforms how we view the scientific endeavor itself. The true mark of progress isn't the elimination of unknowns, but the refinement of our ignorance. As physicist James Clerk Maxwell once quipped, thoroughly conscious ignorance is the prelude to every real advance in science. Those who measure nothing understand this better than anyone. Their work stands as a testament to human curiosity's most noble quality, not the arrogance of assuming we can know everything, but the wisdom to keep searching even when we can't. So the next time you hear about an experiment that returns null results or a theory that raises more questions than answers, remember, these aren't dead ends. They're invitations. The universe may never surrender all its secrets, but in the trying, in the collective effort to listen to its silences, we discover something equally precious: our capacity for wonder in the face of the infinite. The stories of these cosmic pioneers aren't just footnotes in textbooks, they're lifelines thrown to the next generation of scientists staring up at the night sky, wondering if they belong. Picture a high school student in a small town, scrolling through images from the James Webb Space Telescope, their fingers pausing over a distant galaxy. What they're seeing isn't just light from billions of years ago. It's proof that curiosity can bridge the gap between impossibility and discovery. That's the legacy of astronomers like Vera Rubin and Fritz Zwicky, not just their findings, but their refusal to let skepticism extinguish their questions. When Rubin was told women didn't belong in observatories, she didn't walk away. She built her own career path, brick by brick, proving that the universe doesn't care about earthly barriers when it comes to revealing its secrets. For young scientists today, these narratives offer something rare: permission to embrace the unknown. Take Jocelyn Bell Burnell's pulsar discovery, a breakthrough that came not from following a prescribed path, but from noticing an anomaly others might have dismissed. Her story teaches a crucial lesson. Sometimes the most revolutionary science happens when you're willing to chase the glitches, the outliers, the data points that don't fit. Modern classrooms often prioritize tidy answers, but astronomy's greatest hits are written in the margins of uncertainty. When a middle schooler learns that dark matter was first proposed in the 1930s and ignored for decades, they're not just absorbing a fact, they're learning that even crazy ideas can reshape reality if given enough time and evidence. This legacy thrives in programs like NASA STEM internships, where students work alongside researchers analyzing cosmic microwave background data, or in citizen science projects like Zooniverse, where anyone can help classify galaxies from their laptop. The message is clear: you don't need a PhD to contribute to humanity's greatest detective story. When a teenager joins an online forum debating the Hubble tension, or watches a live stream of a neutrino detector's readings, they're not just spectators, they're stepping onto a playing field where the rules are still being written. What makes astronomy uniquely inspiring is its scale of possibility. A kid tinkering with a backyard telescope might not discover a new planet, but they're participating in the same tradition of wonder that led Galileo to Jupiter's moons. The field's history is littered with amateurs who made epochal contributions like Clyde Tombaugh, a farm boy with no college degree who found Pluto using a homemade telescope, or Caroline Herschel, who went from household servant to celebrated comet hunter. These stories demolish the myth that science belongs only to elites in ivory towers. They shout, "Look what happens when you stay curious." Perhaps the most powerful lesson lies in how these astronomers handled failure. When Arno Penziers and Wilson first heard that mysterious hiss in their radio telescope, they didn't celebrate, they groaned, convinced they'd messed up. Their willingness to sit with discomfort, to treat frustration as a clue rather than a dead end, is a masterclass in resilience. For a generation raised on instant gratification, that's revolutionary. It says the answers won't come quickly or easily, but they will come if you keep looking. Now, imagine a classroom where students dissect the Michelson-Morley Experiment not just as a historical event, but as a case study in intellectual courage. Those scientists could have fudged their data to match the expected ether wind. Instead, they published their Null result and changed physics forever. That's the kind of integrity young researchers need today: the guts to report blank screens and unexpected silences, because those might be the cracks where new light gets in. The torch is being passed in real time. Projects like the Asteroid Hunters Initiative invite students to analyze telescope images for undiscovered space rocks, while coding boot camps teach kids to write algorithms that sift through petabytes of galactic data. The next Vera Rubin might be a 12-year-old girl in Mumbai tracking variable stars with her smartphone, or a refugee in a makeshift classroom sketching dark matter distributions on a chalkboard. The tools have changed, but the spark remains the same. That moment when a human brain locks onto a mystery and refuses to let go. These astronomers' greatest gift isn't their discoveries, it's their demonstration that science is a living, breathing adventure. Their careers weren't linear paths to glory. They were messy journeys full of wrong turns, dead ends, and occasional flashes of brilliance. That's the invitation extended to every young mind gazing at the stars. Come as you are. Bring your questions, your doubts, your wildest hypotheses. The universe has plenty of secrets left, and it's waiting for you. The most groundbreaking discoveries in astronomy rarely come from staring at the stars through a single lens. They emerge where fields collide, where physicists argue with engineers, where computer scientists challenge astrophysicists. Picture the team behind the Event Horizon Telescope, radio astronomers working alongside machine learning experts to sharpen the first black hole image, while material scientists engineered mirrors precise enough to detect distortions smaller than an atom. This wasn't just teamwork, it was intellectual alchemy, transforming raw data into cosmic revelation by borrowing tools from disciplines that, on the surface, had nothing to do with black holes. Take the hunt for dark matter as another example. Particle physicists designed detectors deep underground, while astrophysicists map the gravitational fingerprints of invisible mass across galaxies. Meanwhile, quantum computing researchers develop algorithms to sift through noise for faint signals. No single field could crack this puzzle alone. It's like building a cathedral where each craft, masonry, glasswork, carpentry, contributes something essential to the whole. Vera Rubin understood this instinctively. When her optical telescopes revealed galaxy rotations that defied Newton's laws, she didn't isolate herself in the astronomy wing. She sought out particle theorists, knowing the answer might lie in realms beyond her expertise. The magic happens in the overlap. Consider how LIGO gravitational wave detection relied on mechanical engineers creating vibration-free mirrors, while statisticians developed noise filtering techniques originally used for stock market analysis. Or how the James Webb Space Telescope's infrared sensors borrowed technology from medical imaging devices, adapted to peer backward in time instead of into the human body. These cross-pollinations aren't accidents, they're necessities. The universe doesn't organize itself into academic departments. Sometimes the most unexpected collaborations yield the sharpest insights. When astronomers studying the cosmic microwave background hit a wall with interference, they turned to telecommunications engineers who'd spent decades battling signal noise in cell phone networks. The result, filters so precise they could distinguish between Earth radio chatter and whispers from the dawn of time. Similarly, modern dark matter experiments use techniques from forensic science to eliminate false positives, treating their detectors like crime scenes where every stray particle is a potential contaminant. What makes these interdisciplinary efforts so powerful isn't just the sharing of tools, it's the collision of perspectives. A computer scientist might see patterns in cosmic data that an astrophysicist would dismiss as noise, simply because they're trained to look for different signals. The history of science is full of breakthroughs that happened when someone asked, "What if we tried this thing from another field?" Like when radio astronomers borrowed Fourier transforms, a mathematical tool developed for heat flow equations, to unravel the structure of distant quasars. Yet these collaborations aren't without friction. Specialists speak different technical languages. Physicists think in equations while engineers visualize stress tolerances. The teams behind the Large Hadron Collider famously spent years learning to bridge gaps between theorists who wanted maximum collision energy and engineers who had to keep the machine from shaking itself apart. But as astronomer Sandra Faber once noted, the tension between what's possible and what's needed is where real innovation lies. This interdisciplinary spirit is now baked into modern astronomy's DNA. Projects like the Vera C. Rubin Observatory don't just recruit astronomers, they hire data scientists fluent in AI, mechanical engineers who have worked on submarine stealth technology, even philosophers to help interpret findings that might challenge fundamental concepts of time and space. Because measuring nothing isn't just about pointing telescopes at empty sky, it's about building a mosaic of knowledge where each tile comes from a different discipline. And when those pieces snap together, what once looked like emptiness suddenly crackles with meaning. Theoretical physics operates like a cosmic cartographer. It doesn't just map what we see, but sketches the contours of what we can't. When astronomers point telescopes at seemingly empty patches of sky, they're not staring into oblivion. They're testing hypotheses about the invisible scaffolding of reality. Think of it as a dialogue between imagination and evidence. Einstein's general relativity predicted gravitational waves in 1916, but it took a century for LIGO to catch one. That delay wasn't a failure. It was the necessary friction between theory's audacity and experiment's meticulous validation. The dance between these disciplines is anything but orderly. Sometimes theory races ahead, as with string theory's elegant equations suggesting extra dimensions, concepts so abstract we still lack tools to test them. Other times, observations shock theorists into rewriting textbooks. Dark energy's discovery in the late 1990s sent physicists scrambling, forcing them to resurrect Einstein's long-discarded cosmological constant and confront the unsettling idea that empty space itself might repel matter. These moments reveal science's heartbeat, not steady accumulation of facts, but violent leaps sparked by tension between what's predicted and what's observed. Consider how quantum field theory reframes nothing. The vacuum of space isn't passive emptiness. It's a seething quantum foam where particles flicker in and out of existence. This isn't poetic metaphor, it's math that predicts measurable effects like the Casimir force, where unseeable quantum fluctuations push parallel plates together. Theorists didn't invent this from whole cloth. They built on anomalies in atomic spectra and perplexing electron behavior. Conversely, when the Large Hadron Collider confirmed the Higgs boson in 2012, it validated decades of theoretical work explaining why particles have mass. The Higgs mechanism had been elegant equations on paper until engineers built a machine powerful enough to probe its reality. The most fertile theories thrive at the edge of disproof. Take supersymmetry, which proposes every known particle has a heavier superpartner. Initially devised to tidy up messy quantum math, it became a leading dark matter candidate. Yet after years of null results at the LHC, some physicists are ready to abandon it, while others tweak parameters, insisting the right energy level hasn't been probed. This isn't stubbornness, it's how science self-corrects. As Richard Feynman quipped, we're trying to prove ourselves wrong as quickly as possible, because only then can we find progress. What's often overlooked is how theory shapes perception itself. Before Vera Rubin's galaxy rotations, Fritz Zwicky's dark matter hypothesis languished because it lacked a coherent framework. Once theorists linked it to cold, slow-moving particles, experiments knew where to look. Similarly, inflationary cosmology, the idea that the universe underwent exponential expansion in its first moments, transformed the cosmic microwave background from static into a Rosetta Stone. Theorists calculated it should contain specific polarization patterns. When telescopes finally detected them in 2014, it wasn't luck, it was a targeted interrogation of silence. This synergy faces modern challenges. As experiments grow costlier, think 30-meter telescopes or next-generation particle colliders. The pressure mounts for theories to justify their price tags. Some argue we've entered an era of post-empirical science, where theories like the multiverse may never be testable. Others counter that history is littered with untestable ideas that later spawned measurement revolutions. The Higgs boson seemed fantastical in 1964. Neutrino detection was deemed impossible until a nuclear reactor proved otherwise. Ultimately, the interplay between theory and observation mirrors the scientific method itself: guess, test, revise. When Michelson and Morley's null result shattered the ether theory, It didn't halt progress, it forced physics to evolve. Today's theorists crafting models of quantum gravity or dark matter particles are writing the questions future experiments will answer. And when those experiments return more silence, as they often will, it won't mean nothing was found. It'll mean the universe is whispering back in a language we're still learning to hear. The world's deserts, mountaintops, and icy plains tell a silent story of human collaboration, because when it comes to unraveling the universe's mysteries, geography is no barrier. On the high plateaus of Chile's Atacama Desert, the ALMA telescope arrays 66 antennas stretch across 16 kilometers, their dishes tuned to the faint whispers of cosmic dust clouds. But this isn't just a Chilean project. Engineers from Japan designed the receivers, European supercomputers processed the data, and astronomers from Nigeria to Norway analyzed the results. Half a world away, in the frozen darkness of the South Pole, the Ice Cube Neutrino Observatory transforms a cubic kilometer of Antarctic ice into a particle detector, a feat made possible by American funding, German sensor technology, and South African logistical support. These installations aren't just scientific tools, they're monuments to what happens when borders dissolve in the face of cosmic curiosity. What's striking isn't just the diversity of locations, but how seamlessly traditions intertwine. In Western Australia, the Murchison Radio Astronomy Observatory sits on ancestral lands of the Wadjuri Yamaji people, who have read the night sky for tens of thousands of years. When astronomers there detected the oldest known starlight in 2020, they credited both cutting-edge radio telescopes and indigenous sky knowledge that helped interpret the data. Meanwhile, in China's Guizhou province, the 500-meter aperture spherical telescope fast scans for pulsars with a dish so vast it could hold 30 football fields. Yet its operations depend on algorithms developed through international collaborations with French and Australian researchers. The language of the cosmos might be universal, but deciphering it requires every dialect of human ingenuity. This global tapestry extends beyond hardware. When the Event Horizon Telescope captured humanity's first image of a black hole in 2019, the breakthrough relied on 8 observatories spanning 4 continents, with data synchronized to within a trillionth of a second. Mexican astronomers calibrated the high-altitude Large Millimeter Telescope, while Hawaiian teams defended Mauna Kea's summit from snowstorms that could disrupt observations. Back in Massachusetts, a Taiwanese-born computer scientist developed the algorithm that stitched together petabytes of raw data into that now iconic orange ring. No single nation could have achieved this alone, not just because of cost, but because the Earth itself had to rotate to keep the black hole in view, passing the baton from one telescope to the next like runners in a relay race across the planet. The human dimension of this collaboration often goes untold. At the Square Kilometre Array's headquarters in the UK, you'll find engineers from Ghana debugging software alongside Dutch astrophysicists debating dark matter models, while Brazilian grad students share cafeterias with South Korean instrumentation experts. These aren't just colleagues, they're cultural ambassadors. An Indian researcher might explain how ancient Vedic texts described cosmic expansion millennia before Hubble, while a Kenyan astronomer draws parallels between Maasai star lore and modern exoplanet research. The shared goal, measuring what can't be seen, becomes a bridge between worlds, both terrestrial and celestial. Yet this unity isn't without friction. Political tensions occasionally seep into observatory boardrooms, and funding disparities leave some nations' scientists struggling for access. But the night sky has a way of putting earthly squabbles in perspective. When Venezuelan astronomer Maria Alejandra Diaz discovered an anomalous galaxy rotation curve mirroring Vera Rubin's work, she published alongside Iranian researchers despite sanctions because dark matter obeys no borders. Similarly, Ukrainian and Russian scientists continued sharing gravitational wave data even as their governments clashed, proving that curiosity can sometimes transcend conflict. The most profound collaborations often emerge from asymmetry. Take the hydrogen epoch of reionization array Vera in South Africa, where local technicians maintain antennas that probe the universe's first stars, while theorists at Canadian universities interpret the signals. Or the partnership between Peruvian high-altitude communities and Japanese universities, where indigenous knowledge about atmospheric clarity helps optimize telescope placement. These partnerships aren't charity, they're recognition that brilliance is global even if resources aren't. This interconnectedness has birthed a new kind of scientist, the cosmic diplomat. Figures like South Africa's Carolina Erdmann Govender, who spearheads efforts to bring African voices into global astronomy, or Chile's Maria Teresa Ruiz, who fights to ensure her country's world-class observatories benefit local students, aren't just researchers, they're architects of a more inclusive cosmos. Their work ensures that when we finally decode dark energy or capture the birth of a neutron star, the credit won't belong to one nation, but to a species that dared to look up together. The next great discovery might come from a doctoral student in Botswana analyzing data from a telescope she's never physically touched, or a Filipino engineer refining a sensor that will fly on a European Space Agency probe. Because in the end, the astronomers who measure nothing aren't just united by what they seek, they're bound by the shared humility of knowing how much remains unseen, and the collective audacity to keep searching anyway. The universe doesn't care which passport you hold. It reveals its secrets to those who listen closely, no matter where they call home. Every breakthrough in astronomy carries an invisible weight, the burden of how that knowledge might be used. When Fritz Zwicky first theorized dark matter in the 1930s, he couldn't have imagined its potential applications. Today, the same quantum sensors designed to hunt for elusive particles could one day be repurposed for stealth surveillance, turning a tool meant to explore the cosmos into an instrument of terrestrial control. The line between discovery and danger blurs quickly. Consider the lasers used to measure gravitational waves. Their precision, capable of detecting distortions smaller than an atom, could also refine missile targeting systems. Astronomy's most delicate instruments often have dual-use potential, forcing scientists to grapple with a haunting question: can we control how our creations are wielded once they leave the lab? Environmental costs add another layer of ethical complexity. Building the Atacama Large Millimeter Array in Chile's desert required diverting water sources in one of Earth's driest regions, threatening fragile ecosystems. Similarly, radio telescopes like the Square Kilometre Array in South Africa must balance scientific ambition with conservation, as their sprawling antenna fields disrupt migratory patterns and local wildlife. Even space-based projects leave footprints. Rocket launches deposit tons of carbon dioxide into the upper atmosphere, while defunct satellites contribute to the growing orbital debris field. The paradox is stark. To study the pristine universe, we must often compromise the very planet that gives us that vantage point. Then there's the question of cultural sovereignty. The 30-meter telescope's proposed construction on Hawaii's Mauna Kea sparked protests, not just over environmental concerns, but because the mountain is sacred in native Hawaiian tradition. For indigenous communities, the night sky isn't just data. It's a living narrative woven with creation stories and ancestral knowledge. When astronomers dismiss these perspectives as obstacles to progress, they risk repeating colonial patterns of extraction. Some projects now pioneer collaborative models. The Large Synoptic Survey Telescope worked with Chilean indigenous groups to mitigate light pollution's impact on traditional star lore, proving science can coexist with cultural preservation when approached with humility. Funding disparities reveal another ethical fault line. While billion-dollar telescopes rise in remote locations, many host nations see little scientific return. African astronomers often lack access to the data collected by instruments on their own soil, as proprietary rights remain with wealthy foreign institutions. This imbalance perpetuates a form of intellectual colonialism, where the global South provides real estate for discovery without reaping the benefits. Initiatives like the African VLBI Network aim to change this by training local researchers and retaining data sovereignty, but progress is slow against decades of entrenched inequality. Perhaps the most profound responsibility lies in how discoveries are framed for the public. When headlines scream about habitable exoplanets or alien megastructures, they often oversimplify complex findings, fueling misinformation. Astronomers must navigate a tightrope, inspiring wonder without sensationalism, acknowledging uncertainty while combating pseudoscience. The 2017 Oumuamua interstellar object controversy, where some scientists speculated about artificial origins, showed how quickly rigorous science can spiral into media frenzy. Responsible communication isn't just about accuracy. It's about safeguarding the integrity of the scientific process itself. Yet within these challenges lies extraordinary opportunity. The same international collaborations that build telescopes can model peaceful cooperation across borders. The environmental toll of observatories drives innovation in green engineering, from solar-powered radio dishes to biodegradable satellite materials. And by centering indigenous knowledge, astronomy could evolve beyond Western paradigms to embrace diverse cosmologies, enriching our understanding of the universe through multiple lenses. The ethical dilemmas won't disappear with better technology or policies. They're inherent to the act of exploration, reminders that every time we reach outward, we must also look inward. Because the true measure of progress isn't just what we learn about the cosmos, it's who we become in the process. As we stand on the threshold of ever grander discoveries, from mapping dark matter to deciphering cosmic inflation, one principle remains clear: the stars belong to everyone, but the responsibility to protect their legacy belongs to those who study them. There's a moment, fleeting but electric, when an astronomer's screen flickers with data that doesn't make sense. A blip where there should be silence, a gap where there should be a signal. It's not frustration they feel in that instant, it's exhilaration, because buried in those inconsistencies might be the whisper of something extraordinary. This isn't just about career milestones or published papers. It's the raw, childlike wonder of peeling back the universe's layers and glimpsing something no one else has seen. When Vera Rubin first noticed stars orbiting galaxies at impossible speeds, she didn't groan at the anomaly. She leaned in, heart racing, sensing the tectonic shift beneath her feet. That thrill transcends the lab or observatory. Picture the team at LIGO on the morning of September 14, 2015. After decades of silence, their detectors had picked up a chirp, a vibration so faint it shifted their mirrors by less than 1,000th the width of a proton. As the signal's waveform scrolled across their screens, matching Einstein's century-old predictions, the room erupted not in cheers but in stunned silence. One physicist later described it as seeing a ghost you've spent your whole life chasing finally step into the light. What kept them going through years of null results wasn't just funding or professional obligation. It was the addictive possibility that today might be the day the universe decides to speak. This joy isn't reserved for earth-shaking discoveries. Sometimes it's in the quiet validation of a hunch, Take the graduate student combing through data from the Kepler Space Telescope, spotting the faint, rhythmic dimming of a star that signals an exoplanet's transit. Or the amateur astronomer who notices a pinprick of light where none existed yesterday, a supernova flaring to life millions of light years away. These moments share a common thread, the visceral satisfaction of adding one more piece to the infinite puzzle, however small. What's fascinating is how this emotional drive shapes the scientific process itself. The late astrophysicist Vera Rubin once confessed she'd sometimes delay analyzing her galaxy rotation curves, savoring the anticipation like a child saving the best bite of dessert for last. Modern researchers describe similar rituals waiting for sunset at remote observatories, the ritual of brewing coffee before checking overnight data, the collective gasp when a simulation finally matches observation. Science may be methodical, but its heartbeat is undeniably human. This emotional undercurrent explains why astronomers persist despite the odds. Jocelyn Bell Burnell endured freezing nights at Cambridge's radio telescope, her fingers numb as she manually analyzed miles of paper charts for the pulsar signal she'd eventually find. The teams hunting dark matter today spend years calibrating detectors only to see them come up empty, yet they return, refining their methods because the chase itself is intoxicating. There's a term for this in psychology, flow state, that immersive focus where time dissolves in the face of meaningful challenge. Astronomers don't just experience it, they build careers around it. The joy of discovery also thrives in collaboration. When the Event Horizon Telescope unveiled humanity's first black hole image, the global team didn't just share credit, they shared awe. Researchers from 20 countries described the same surreal feeling, staring at that fiery ring, knowing they'd collectively stretched the limits of technology to glimpse a shadow cast by gravity itself. In an era of hyper-specialization, these moments remind scientists why they entered the field, not for isolated brilliance, but for the shared privilege of revelation. Perhaps the most surprising aspect is how this passion persists beyond professional circles. Amateur astronomers still contribute vital comet and supernova discoveries using backyard telescopes. Online platforms like Zooniverse let anyone sift through galaxy surveys or classify Martian terrain, proving you don't need a PhD to feel that jolt of "I found something." This democratization of discovery underscores a profound truth. The drive to explore isn't taught, it's innate. We're all hardwired to seek patterns, to question emptiness, to find meaning in the unknown. At its core, this joy is an antidote to cynicism. In a world often fractured by disagreement, the act of discovery remains unifying. Whether it's a tenured professor or a high school student staring through a telescope for the first time, that spark of recognition bridges divides. Because when you've spent nights chasing a single pixel of light in a sea of noise, or years building an instrument to listen for echoes of the Big Bang, you're not just doing science, you're reaffirming humanity's oldest, noblest impulse, to look beyond ourselves and wonder what else is out there. And sometimes, against all odds, to actually find out. The astronomers who spent their lives measuring nothing didn't just change science, they redefined what it means to be human. Think about it, every time you gaze at the night sky, you're seeing it through their eyes. Those faint stars, Hubble proved their galaxies, the empty blackness between them. Rubin showed it's teeming with dark matter. Even the static on an old TV, that's the echo of the Big Bang, a discovery born from Penziers and Wilson's refusal to dismiss an annoying hiss. Their legacy isn't just in textbooks, it's woven into the fabric of how we understand our place in the cosmos. What makes their stories so powerful isn't just the discoveries, but the defiance. These were people who stared into the void and whispered, "Tell me your secrets." When the scientific establishment laughed at Fritz Zwicky's dark matter theory, he kept publishing. When Jocelyn Bell Burnell's male advisor took credit for her pulsar discovery, she kept researching. They weren't just collecting data, they were fighting for the right to ask questions others deemed foolish. In a world obsessed with quick answers, their lives remind us that the most profound truths often hide in the gaps, the silences, the places we've been taught to ignore. This mindset, this relentless curiosity, is their greatest gift to the future. Right now, somewhere, a grad student is poring over a dataset that doesn't make sense. A telescope operator is staying up till dawn, chasing a blip that might be nothing. A theorist is scribbling equations that could upend everything we know about dark energy. They're standing on the shoulders of giants who taught them one crucial lesson. Progress begins when we dare to take nothing seriously. So the next time you hear about an experiment that came up empty, or a theory that challenges common sense, remember, that's not failure. That's how science moves forward. The universe's greatest mysteries won't be solved by those who play it safe, but by the ones willing to risk everything on a hunch, a glitch, a whisper in the dark. And who knows, the next revolutionary idea might be hiding in your own what if. If these stories ignited your curiosity, you're already part of this grand tradition. Hit like if you're inspired by these cosmic rebels, subscribe to join us as we explore more mysteries, and drop a comment below. What's the cosmic nothing you'd love to measure? The adventure doesn't end here. It's